Off air. Oh, there we are. Hi, everyone. I'm Marissa here at the National Weather Service in El Paso, and today we are going to be teaching teachers how to teach the weather. This came about because we were teaching students about basic weather concepts that happen in the TEACS tests, and some teachers asked us maybe if we would teach them first and then their students, so here we are. Like I said, I'm Marissa, and my partner today who is going to kick things off and teach you all those basic weather concepts is meteorologist Jason Laney. Jason?
All right, very good. Well, first of all, I think I've met Raul once before. I got a little surprise wake-up call at home on my cell phone. So this is what I look like outside of bed, obviously. So at any rate, hopefully I make a better impression this time than last time. I want to welcome you two. We've got two. We are expecting possibly one other teacher to join us here today. And we are broadcasting this live right now on our YouTube channel. There are some other people around the area that kind of want to see what we're talking about, but didn't actually join in for the actual hangout here, so they're going to be part of that as well. So I'm going to ask Marissa to go ahead and get our slides ready, and I'll step you through these. This is somewhat informal, and we will have a chance to kind of talk about some of these concepts. As Marissa mentioned, we are basically trying to hit some of the high points for the TEACS testing here. And just a little background on me. Before I came to the National Weather Service, I spent 22 years working in television. Yeah, I was one of those guys. And to go along with that, I also spent 8 years teaching at the university level. And many of my students were just like you guys. They were actually teachers that were getting their continuing education credits. And they wanted to learn a little bit more about the weather in order to be able to more or less teach it to their students with a little more confidence. So that's what we're going to try to do here in 30 minutes today. Cover basically an entire semester's worth of stuff. So we're calling this Teaching Teachers, the Weather Basics. And there are a lot more weather basics than what we have for you today, but I want to hit some of the high points. And we're going to begin things off by taking a look way up in the sky. And we tell everybody that it all begins with the sun. And you're probably thinking to yourself, yeah, I know, the sun's important for weather because sunny days get hotter and cloudy days, of course, are a little cooler like we've got going on outside right now. But it's so much more than that. The sun really drives all weather events that happen at the Earth's surface. And the key to all of this is what we call uneven heating of the Earth, because the sun doesn't heat the Earth the same in all locations. As a matter of fact, you may find this a bit of a surprise. The sun doesn't heat the air at all. Now, I know you see sunny days, the air gets hot, and on cloudy days it's a little cooler, but it's a little more than that. Here's the way it breaks down. We talk about the sun's radiation as what's called long-wave radiation. Now, honestly, all radiation, all the forms of radiation, the entire electromagnetic spectrum comes from the sun. But the greatest concentration of the sun's radiation is in what we call the shortwave wavelengths there, and that's going to include the visible light that we see coming through the sun. And I think we hopefully get to the next slide there, Marissa. It's going to help us out just a little bit. This shortwave radiation, for the most part, tends to pass through the atmosphere. It's as if a window. If you've ever seen what happens with a greenhouse or your car, the energy from the sun passes through the window and it begins to heat up the interior parts of the car. Well, the same thing happens with our atmosphere. The incoming solar radiation tends to basically pass directly through the atmosphere where it gets absorbed at the Earth's surface. And there's several laws of radiation. If you've taken some physics classes, you've probably heard before. One of the laws of radiation says that a good absorber is a good emitter. So what happens is while the atmosphere does not absorb the incoming solar radiation, the Earth does, and the Earth begins to heat up. That's just like a frying pan on top of the stove. As the pan gets hotter, it begins to radiate that heat back. And that heat that comes back is what's known as sensible heat. If you've ever held your hand up over a flame or over a hot pan, you can literally feel the heat beginning to radiate up towards you. That is infrared radiation. That is heat radiation. And that is the type of radiation that the Earth gives off. So while the atmosphere or the air around us, it doesn't do a good job absorbing the sun's radiation, it does a marvelous job absorbing radiation that comes from the Earth. So that's why my little schematic on the left side of the screen here shows you you're going to find your warmest temperatures of the air right near the Earth's surface. Then the higher you go in elevation, obviously it gets a little colder. So one way to understand heating is you have to understand the difference between the long wave solar radiation, or the short wave solar radiation, and that long wave radiation coming from the Earth. Now, I talked about this thing called uneven heating. Obviously, the Earth heats because of the sun. The sun heats the Earth. But the sun is so large, it's so immense in comparison to the size of the Earth, that incoming solar radiation is basically received in parallel rays. But notice what the Earth looks like. Just like what Christopher Columbus found out, the Earth is not flat, it's not square. The Earth is nice and round there. So what happens, the incoming solar radiation right at the center of our globe there comes in at the most direct angle possible. That's going to be about 90 degrees, the most vertical rays. But rays from the sun that are absorbed in the high latitudes up towards the North Pole, down near the South Pole, well, those come in at a lower angle. And lower angle means less radiation is received. So equatorial regions get more direct radiation, they get hotter. Polar regions get less direct radiation, even though it's the same sun, they get colder. So just for that reason alone, we notice that the Earth heats unevenly. Up north it's cold, way down south it's cold, and in the middle of it all, through the tropics near the equator, it turns out to be a little bit warmer. But that's just another part of the equation. It turns out on an axis and tilted on its axis. Now the next slide that I want to show you kind of shows the way that the radiation is coming into the Earth, but I have not tilted the axis just yet. I put the axis straight up and down perpendicular. And this is basically similar to the way that radiation is received on the first day of spring or on the first day of fall. You'll notice I've got the two equinoxes listed there for you. Well, on these particular days, the sun angle at the equator is 90 degrees. That is the most direct sun angle possible. That means maximum radiation is being received at the Earth's surface. Notice how the numbers trail off as you head up into the northern hemisphere. You get up to the Arctic Circle, and the sun angle is only 23.5 degrees. That's only a fraction of
Mr. Jason, give me a second. Everyone, if you guys will just mute your mics, we can't mute them from our end for some reason. So at the very top, there you go, Priscilla. Thank you. I see you, Raul. Rosalie, if you guys can mute your mic. I don't know if you guys can hear us. There you go. Perfect. Okay, Mr. Jason, go ahead.
Okay, I get to go back. I'm sorry, I couldn't hear all that, so I didn't know what was happening. But at any rate, when we're talking about what happens with the sun's rays, obviously the energy absorbed in the higher latitudes, that would be where the United States is and up around Canada, is much lower sun angle at any given time of the year than towards the equatorial regions. And that makes sense why we're not quite as hot as they are at the equator. But remember I said that the Earth is tilted on its axis. Let's go ahead and tilt things now into the reality of what goes on. And the tilt of the Earth's axis, or the axis of inclination here, is 23.5 degrees. And that's going to be a pretty important number because, as you'll notice, the highest sun angle is 90 degrees. This case, it's going to be over the Tropic of Cancer, which, if you look at a globe, happens to be right at 23.5 degrees north latitude. So that's that tilt that we have as far as the Earth on its axis. So what we're looking at here is the first day of summer, and the northern hemisphere is tilted towards the sun. This is a perfect explanation as to why when it's summer in the northern hemisphere, down to the south of us in South America, it's winter. Look at that. The Tropic of Capricorn only at 23.5 degrees sun angle, and that's the maximum sun angle at midday, as opposed to up towards 6.5. So believe it, on the first day of summer, even though we're not in the tropics, we're receiving more solar radiation than some areas that are a lot closer to the tropics in the southern hemisphere. Now let's flip things just a little bit, and in flipping things, I'm going to give you just the opposite and show you what happens here. We're going to go from the first day of summer, when the northern hemisphere was tilted towards the sun, to the first day of winter, when the northern hemisphere is tilted away. Look at those sun angles up in the northern hemisphere. They're rather low. Less incoming solar radiation, less heating. That's the uneven heating, and that's the reason for our seasons. Now, one thing I want to caution you on, you've seen the images. I started with the axis straight up and down, then I tilted it towards the sun, and then I tilted it back away from the sun. It turns out that the Earth's tilt, the axis, it doesn't rotate it like that. No, the axis is a permanent thing, that tilt. The next slide is going to show you how we end up with our seasons. Because the Earth is always tilted in the same direction on its axis, you have to remember the Earth actually has two types of motions. One motion is called rotation. It rotates on its axis, and it takes about 24 hours to rotate all the way around on its axis. That's day and night. That creates uneven heating if you think about it. The other thing that it does is it revolves, and the Earth literally revolves around the sun. And notice in each of these situations, be it winter, spring, summer, or fall, the Earth is tilted the same on its axis. But when it's on one side of the sun, the southern hemisphere is pointing towards the sun. That would be winter for us. And when it rotates, or revolves, that is, around to the other side, all of a sudden the northern hemisphere is facing the sun. So this gives us the impression that where the sun is located migrates into the northern hemisphere in the summer, into the southern hemisphere during the winter, and then back across the equator for the first of spring and fall. But really, it's because the way the Earth revolves around the sun that creates all that. So all of this is going to lead us to this thing called unequal heating. Okay, it's unequal heating because the Earth is round. It's unequal heating because the Earth is tilted. It's unequal heating because the Earth makes its way around the sun, and different hemispheres get more direct radiation at different times during the year. But believe it or not, even areas that get the exact same amount of solar radiation may end up heating differently. That's what we call our differential heating of land and water. And what we have found is that land tends to absorb solar radiation much more rapidly than the water does, so land heats up faster into higher temperatures. Imagine this. You've been to the beach, right? Hopefully you go to the beach in the summertime. That's when most folks do. And you walk out there and you walk it across the sand. That's the land portion. And if you're not wearing some slippers or flip-flops, chances are on a sunny day that sand is burning the bottom of your feet. It gets really hot. Well, you take a few steps and put your feet in the water into the ocean, then all of a sudden things are nice and cool. Well, those areas are what? Just a few footsteps away. Obviously, one is hotter than the other. So that gives credence to the point that we're talking about here, that land heats up faster than water does, and it gets a lot hotter than water. Land also cools off faster, so at nighttime you walk across that sand, it may feel kind of cool, but put your foot in the water in comparison may actually feel kind of warm. So we have differential heating of land and water that leads to the same process of some areas get more intense heating than others. And remember, it's the heating of the Earth that's going to determine the heating of the air that's just above it. Now, what does all of this do? We understand that, yes, the sun is going to drive the heating, but I said that the sun responds to lots of things in weather. Everything in that weather for that matter. Well, here is the reason I pointed out. Uneven heating at the Earth's surface leads to uneven pressure distributions. And this is one of the points that you're going to talk to your students about. That's going to be the concept of high pressure and low pressure. So what I've done is I've given you a map here that has, well, it's a basic looking weather map, some semi-permanent pressure distributions here. And notice where the H's are, at least in the middle latitudes. That would be the United States and on into parts of Europe and Asia over there. The L's, or the lows, happen to be over the land. What does the land do? It gets hotter. Look at where the H's are, the high pressure. They tend to be congregated over the oceans in general. These are areas that are obviously a little cooler. So it turns out that that uneven heating between hot sources and cold sources is going to create a difference in pressure. Our next slide is going to show you that just a little more clearly, and you'll be able to see that I've put the cool side of things under the high pressure where things are heating up less, and the warm side of things under low pressure where things are heating up more. And so the sun actually has a big play, or a big part, or is a big player in the pressure distribution at the surface. And one of the things that we have learned through meteorology is that pressure determines the movement of the air. Simple definition. What is wind? If we were playing Jeopardy here, the slide would have said it's the movement of air molecules, and the correct answer would be, what is wind? Well, wind, or moving air, is created because differences in pressure, which of course were created by differences in heating. Air tends to move from high to low pressure, and once air gets on the move, you start talking about wind, of course. So now we've talked about the sun's relationship to heating, we've talked about the sun's relationship to pressure, and we've in a roundabout way talked about how the sun can influence the movement of air, well known as the wind. Now we'll come back into that in just a moment. Let's look at this high and low pressure stuff a little more closely. In high pressure, it turns out that air aloft is sinking. And what we're literally doing in high pressures, we're taking air molecules from up here and we're moving those air molecules and compacting them down at the surface. That creates high pressure, or a greater density, more molecules in a simple volume of air near the Earth's surface. But as these things begin to collect at the Earth's surface, they can't stay in one place, so they get pushed out. So at the surface, the air tends to flow away from high pressure. I'm using the fancy word diverge here, but we can say that air flows out of high pressure, and consequently it flows into low pressure. And in doing so, we end up with convergence, or air coming together. When air molecules come from one side, come from the other, and they collide, and they can't go down because the ground is blocking them, they have no other course of action but to rise. So you start rising air currents in low pressure. So you see there's a complete opposite of these two. High pressure air sinks and moves out. Low pressure air comes together and rises. And that rising air current is actually pretty important because that can create things like clouds. So we have associated weather with each of these pressure systems. One of the ways we like to teach it to children is say, hey, you know what H stands for? Yeah, we know it stands for high pressure on the map, but we also know that H stands for happy weather. Because usually when you have high pressure, you're going to end up with mostly clear skies, calmer winds, because the wind's just getting started. If you have a drag racer on the racetrack, when he first starts and leaves his position, he's not moving anywhere near as fast as he is when he reaches the finish line. That's the way it is with air that moves out of high pressure towards low pressure. So we end up with calmer conditions and generally dry weather. And remember, if you've got sun, and on the land especially, the land's going to heat up fast, so high pressure can give you some rather high daytime temperatures, but at night it can get kind of cold. And because weather is kind of tied into this whole concept of opposites, let's look closer at what low pressure gives us. And again, we can tell our students that yes, low pressure starts with an L on the map, and for the meteorologist, an L means low pressure. But for the rest of us, it generally means lousy weather out there. Because the air is rising, it's going to begin to cool off, and condensation will take place. And the condensation will lead to the development of clouds.
Pick it up right off the surface.
Then we end up, hold on one second. Marissa, I can hear you. I'm sorry.
I'm sorry. We were having a little weather issue here.
Okay, it's all right. It means that we're going to get cloudy skies, and generally with the clouds comes precipitation, so low pressure is usually associated with the development of rain and or snow. And as we'll see on a coming weather map, a lot of times when low pressure leaves us, the cold air tends to move in. But one of the keys to low pressure is it gets kind of windy. Remember the drag racer that I talked about there? He may start off at a slower speed, but when he reaches his final destinations, he's at maximum velocity. So as the air flows into low pressure, it tends to flow a little faster. So this is basically what your typical weather map's going to look like. You've got a high pressure area where it's colder, a low pressure area closer to the areas where it's warmer. That kind of goes hand in hand with one of the slides we looked at. But notice coming out of the low pressure, we've got a couple of drawn lines here. One is blue with circles, one is red with semicircles. Well, the red with semicircles represents a warm front, and the blue one represents a cold front. Now, just right quickly as we get into fronts here, the name gives it away. It is the front side of something. That's why we call it a warm front, not a warm back. We're not talking about the backside of anything here. That would not be nice, especially if we're talking to students in school. So when we talk about a warm front, we're talking about the front side of warm air. And if we go back to this picture, you can see the warm air there, and then the little red line is right on the edge of it. Well, the direction that those semicircles points is the direction that the air is moving. So in this particular case, you can probably imagine the warm air is out of east and on its way up into Arkansas and northern parts of Oklahoma. Well, just the same, a cold front represents the front side of colder air masses. And those little triangles we're looking at, well, they point to the direction the cold air is moving. So to happen in this sense, the cold air that's over into West Texas, and in time it's going to continue its migration a little further to the east. a little closer at this idea of and cold fronts that we've seen on this map. And basically, it's a boundary at the Earth's surface. That'll be our next slide there. It's a boundary where cold air is separated from warm air. Now, a couple of things to note about warm fronts and cold fronts. Because cold fronts are the front side of cold air is much more dense than warm air is. Because cold air tends to want to segregate at the Earth's surface. Lots of molecules. Warm air wants to rise and escape, so you get a lesser concentration of molecules there. Well, because cold air is more dense, so cold fronts move more rapidly. Warm fronts, they tend to move a little more slowly. And in both cases, what is going to happen, you're going to get like a little wedge there, like the wedge that you would hold your door step open with. You're going to get warm, moist air that goes up over cold air. Let's go back to this image, and you can see it's a gentle slope with the warm front, but it's a very sharp edge with the cold front. So we have gentle lifting with a warm front. So ahead of a warm front, you're likely to get a pretty good line of some cloud, but they're usually the clouds or stratus clouds to produce a lot of precipitation. On the other hand, because fast they lift the air, cold fronts are almost associated with weather, and most of the time, especially in the warmer months, they're going to be associated with the development of thunderstorms. So let's put this back together on a weather map, shall we, and watch as one cold front moves across. Remember, the cold front's the front side of colder air. So in this case, ahead of the cold front, the air's nice and warm. We'll call this Monday. Step ahead to Tuesday, and all of a sudden, areas that have been passed by the cold front tend to cool off. Areas ahead of the cold front are still warmer. And by Wednesday, as the cold front clears the area, well, at that point in time, we're going to be looking at much cooler air area-wide. But cold fronts do more than just cool the air down when they move through. Remember, the lifting along the front creates the clouds and the thunderstorms. So on Monday, the storms are entering West Texas. By Tuesday, they've migrated across half the state, Dallas, San Antonio getting the storms. And by Wednesday, things are clearing out in the west where it's colder, but still stormy there along the coast. So cold fronts, warm fronts, and working with high pressure and low pressure in the weather map, they all kind of go together there. But remember, cold fronts move faster, and cold fronts tend to produce the most intense precipitation. Now, how did we get that precipitation? How did we get the clouds? Well, we talked about how the sun influences high and low pressure, and when high pressure the air departs, low pressure it comes together. But remember, the air is rising in low pressure, and as the air rises, what is the temperature the higher up you go? Obviously, it's a little colder because your warm source is the Earth. So you get away from it, it's going to start getting colder on you up there. Well, as the air gets colder, the water molecules that are suspended in the air condense and they form cloud. Let's take a look at molecule. I like to call it an amazing molecule because water, it is the only substance, it's H2O as we know it, but it is the only substance that exists naturally on this earth in all three states of matter, solid, liquid, and gas. Now, we can get other molecules to exist in solid, liquid, and gas, but sometimes you have to add extra pressure. Sometimes you have to reduce the pressure. You have to have heat that is greater than the heat that naturally occurs at the Earth's surface. Well, water, it can happen in all three states, and it does. And it's because of that that water cycle that all the students sing the little song about can happen. If it weren't for that magical molecule known as water and its ability to be solid, liquid, or gas, given the temperature and pressure that we experience on Earth, the water cycle couldn't happen. And so what happens is the Earth heats, you get evaporation. The evaporation becomes moisture in the air. We call it water vapor. Well, high pressure causes the air to sink, but low pressure causes the air to rise. So when we get areas of low pressure, that moisture rises, condensation takes place. Eventually, it returns as precipitation, and the cycle goes over and over again. So as you're teaching the water cycle to the students, they'll learn things like evaporation. That's what happens when water leaves like lakes and oceans, or maybe even our skin as we perspire. But plants also have a tendency to release quite a bit of water vapor to the atmosphere. They do so by tapping their root system and pulling up groundwater. And then as the plants get hot, they kind of do what we do. Transpire. It's called transpiration. So you'll notice on the water cycle here, we have evaporation from oceans, lakes, and streams. we have transpiration from plants. That's the scientific term, but it all leads to adding the water vapor to the moisture. So as you cover your topics on the water cycle, along with the cute little song, which I always forget all the words to. I guess it happens the older you get. It is kind of fun to kind of talk about those different states of matter and how it can all happen. And another thing that you're going to be tasked with talking about in your classes is going to be hurricanes. The hurricane I call the greatest storm on Earth. Let's take a look at why that might be. But before we do that, while I may call it the greatest storm on Earth, people call it different things in different parts of the world. For storms that affect the central and eastern Pacific and the Atlantic, well, they're hurricanes. They are named after the Carib god Huracan, which was, I don't remember all of the stories that go with that, but that's where the name came from. But in different parts of the world, they call hurricanes different things. In the Indian Ocean, they're called cyclones. Off the coast of Japan in the western Pacific, they're called typhoons. Well, you can read, and you know the one that won the story. Well, those crazy folks down in Australia, they do everything at the beat of their own drum. They call hurricanes willy willies. And believe it or not, no matter what you call it, it's still the same thing, and it still turns out to be the greatest storm on Earth. So let's look at this storm and what does a hurricane need to form. And the main ingredient that a hurricane needs to form is warm ocean water. That's why hurricanes don't form over the land. There's no warm ocean water on the land. But out in the tropical oceans, during the summer months, when the water temperature reaches about 80 degrees Fahrenheit or higher, that's when you start to produce a ton of evaporation. You get a lot of water molecules in the lower atmosphere. And that warm, moist air will begin to converge near the center. Notice what's at the center of that hurricane. The letter L, lousy weather. Remember, this is an intense area of low pressure. As a matter of fact, this thing is a little more intense and stronger than most low pressures that move across the continental United States. So it tends to do what low pressure does. It sucks the air into the middle of it. That air converges, it rises, it condenses out, and you get these walls of clouds and storms. And generally, the winds aloft aren't that strong at all. So hurricanes tend to move at a fairly slow pace. So let's look at the hurricane from another view, what I like to call the anatomy of the hurricane, and there are three major parts that you'll want to focus in on. One is the very center of the storm where the low pressure is located. That's the eye. The other is the area of storms that surround the eye, known as the eye wall. And then finally, there's other series of storms that surround the center, but at a greater distance, known as spiral rain bands. So we'll zoom in on these and talk about them a little more just to give you some idea of what each of these consists. The eye itself actually contains very light winds. And that's kind of hard to fathom because this is the center. Intense low pressure, the greatest storm on Earth, but in the middle of it all, the winds are light. Sometimes the skies are clear, even though we have this very low pressure. It turns out the most deadly and destructive part of the storm is right beside the eye, on either side of it and surrounding it. That's the eye wall. That's literally a wall of thunderstorms that develop around the center of this thing. These have intense winds. It's where your strongest winds are going to be found. It's where your heaviest rain is going to be. And there's also one other aspect of damage that hurricanes do that's called a storm surge, and that's actually the deadliest part of a hurricane. That is literally a wall of water, like a high tide, a wall of water that comes crashing ashore. And if you've ever done a belly flop in the pool, you know that when you hit that water's pretty hard and it stings. Well, imagine you're falling at what, 6, 7 miles per hour at most as you hit that water. Imagine a wall of water hitting you at the same speed that the winds of a hurricane are, 80, 90 miles per hour. That would be doing like an 80 or 90 mile per hour belly flop. That's not going to feel good, and that's why you get so much damage right there at the eye wall when the storm comes in. But even before that can affect us, we have these spiral rain bands, which also produce heavy rain, strong winds, and these tend to spawn smaller tornadoes. So you kind of get it all with a hurricane. So that's why we do call hurricanes the greatest storm on Earth. Maybe not the greatest show on Earth. Somebody else calls their show that. Now, one of the questions that we get, and this is probably a little in depth for what you'll be teaching to a 5th or 4th grade class or 6th grade class, but when you start talking about this thing, and the minute you tell a student that the center of the hurricane, the winds are calm, it's just human nature for them to ask you the question why. And chances are you guys may be thinking the very same thing. Why is it calm then if that low pressure is so intense? Well, it all has to do with this physical thing called the Coriolis force. Now, before we go too far, I'll give you the definition of Coriolis force. It's basically an apparent deflection to the right of motion of any free-moving object in the northern hemisphere. Now, let's just wipe that all out of our minds and think about this. A deflection, a turning to the right. Well, in this case, in low pressure, the air is actually turning the other direction, but it is turning into the low pressure. So instead of the air flowing directly into low pressure so that it would collide right at the very middle, as it comes in, it kind of turns a little, and this one turns a little. And it turns out that they bump into each other before they ever make it to the center. They begin to bump into each other around the edges of the circulation, and that's what these arrows tend to show on the left-hand side there. So it's all due to that air not flowing directly into low pressure, but flowing into low pressure in a counterclockwise direction in this sense. And that is going to be the area of the eye wall. So on the right, you see where the air collides and comes together. You get those rising currents. And so that is why your strongest winds and biggest storms are right on the edge of the center, but in the very center of it all, things are kind of blocked. It's like a literal wall. That's why they call it an eye wall, because it's protecting the interior of the storm from all of the strong winds that can come in. So that's kind of interesting, and I know what you're thinking. You're saying, hey, I'm looking down on this, Jason, and counterclockwise is to the left. And if you were paying attention, I said it's an apparent deflection to the right of the path of motion. Well, think about where we are. You were looking at that from the way God would see it, looking down on it. Think about where we are underneath it. And from underneath it, looking up, it is a deflection to the right of the path of motion. So a little tricky there. It's all about your perspective and where it comes from. But Coriolis force, that's why the center of the hurricane is actually calmer. And the last topic we cover here is weather and climate. Now, people tend to use this interchangeably, and we teach this class to students in Spanish as well. We talk about el clima, el tiempo, and if you've ever watched, if you speak Spanish and watch any of the Spanish broadcasts, it is kind of used interchangeably. But the truth of the matter is weather and climate are completely different. Weather is the state of the atmosphere at any given time and place. So I like to say weather is what's happening right here, right now. And the weather that's happening in El Paso right now is probably different than the weather that's happening in New York City right now. So you get the idea, weather is right here and right now. Climate, on the other hand, climate is defined as the sum total of all weather. It includes averages and extremes. So the way I like to talk about this, say you've got a family member who lives in another part of the country, sunny California. They're coming to visit you in El Paso, and they say, yeah, El Paso's in the south. I'm coming in January. It's going to be warm, right? You know what you're going to tell them? You're going to say, even if you're talking about this Thanksgiving or even prior to that, you say, hey, you better bring a coat when you come in January, because usually it can get kind of cold in El Paso. And that's the idea of climate. It's generally an average, but it can also include extremes. You can tell them, yeah, January it can get cold. I can remember one day when it got down to 10 degrees. That's an extreme. But then in the next breath, you'll tell your family member, I remember one day when it got up to 75 degrees. So that's all climate. Climate's kind of history and averages all put together, but weather is a specific happening right here and right now. So to simplify things, we say, is it news or is it history? If it's news, something you can talk about in a generalization, or to talk about that's happening right now, that is weather. But if it's history, kind of a generalization of what has happened in the past, we call that climate. So one other way to think of weather and climate, and this one's kind of neat, weather, climate, that is what you expect. That's when you tell someone coming to an area what you think might happen in advance. Weather is what's going to happen when they really get there. So climate, what you expect. Weather's really what you get. So you can think in terms of news and history, or you can in terms of what you expect and what you get. Remember, weather happens here, right now. And climate is kind of a total of all weather for any given place or any given region, all kind of put together. So we've talked about a lot of stuff here. We talked about uneven heating of the sun and the earth, how the sun heats the earth heats the air. Because the earth heats differently, we get pressure distributions. Because we get pressure distributions, we get air currents moving differently, and rising air, and we get condensation, we get the water cycle, we get these things called fronts and air masses, warm fronts and cold fronts. And then, of course, you put them all together, you get some pretty violent storms there with hurricanes and tornadoes. And these are all things that you're going to be tasked with teaching your students coming up here over the next couple of months. So hopefully I was able to put a little different spin on it, at least in your mind, so you can kind of visualize things in a little different way, because really when it comes to teaching our children about weather, it's how we can best relate things to them in a way that they're going to be follow. So we wanted to have a chance to speak with you, the teachers, and kind of do the same thing with you, kind of just lay it all out in a very basic and simple and informal way. And we really like the fact that we can use these Google Hangouts to do so, so that not only do I get to talk to you, now I know we've asked you to mute your microphones there along the way, but now it's time for you to unmute those things at will. And any questions that you may have come up with, of course, we do have our email addresses here, and we're more than happy to answer things a little later on down the line as questions come up, and hopefully we can give you some better insight on how to talk about some of these topics. But if anything happens to come to mind right now, we'd love to hear from you. So I'm going to let Marissa show her pretty face again. She can turn off the slide. There she is. And I'm going to let her take over.
Thanks, Mr. Jason. Thank you, Jason. I don't know, I was fascinated. Every time I watch this, I'm like, oh my gosh, I learned something new. I don't know if you guys have any questions. Priscilla, do you have anything you wanted to go for now? You can email us.
No, I think that's pretty good. I think it was very good information, and it was kind of like a refresher for what's going to be coming up these next couple weeks.
Yeah, you guys are going to hit the ground running soon. So if you have any questions, just feel free to email us, and I will get you guys the slides, so that you know that. And then this will also be on YouTube. It was recorded and archived, so you all can go back to it. And then we're going to actually start doing some YouTube videos that will help supplement this material. You know, certain ones just on hurricanes, certain ones just on air pressure, so that y'all can go back to those and also use those in your classrooms. And those will be accompanied by some activities that you can do in your classroom to help really solidify this for the TEKS test. Raul, did you have any questions?
Not at this time, no, ma'am.
Okay, perfect. And then Rosalie, I know you guys can hear me and I can't hear you, but if you type your question in the chat, I can answer it, or you can email myself, Tim, or Jason at any time.
I hope you can hear us.
Oh, I can hear you. Okay, I thought I couldn't hear you. There you are. Do you guys have any questions?
You can't see the 50 people we have here.
Oh, you have 50 people there?
How many?
We have trail mix and cold water.
Oh, you guys should have come to us.
Water.
Oh, man. Well, we're glad you guys joined us. I'm sorry that we can't see you, but if you let me know or let Tim Bryce know how many copies of the PowerPoint you need, we can get that to you.
That's great. Thank you.
Okay, well, thank you, everyone, for joining us. We're going to end the Hangout. Hope to see your classroom soon. Bye.
Thanks, Tim. Bye.
Bye-bye, everybody.
Bye.